Oh, yeah. Now we've reached my favorite topic that we've done so far this year because, boy, this has implications that go so far through the rest of the year. What you're going to learn today is going to take you right through to the end of the year to explain how pretty much everything in chemistry works. This is topic 5.03, electron configuration. It's the first clue as to how atoms stick together to form compounds. Let's get started. Now, today you're going to be learning several different configurations based on the location where electrons can be found. Now, the most general location you can find an electron, the most non-specific location, is principal energy levels, also known as shells. Shells are made up of sublevels, and there's an electron configuration for that as well as shells. And sublevels are made up of orbitals, and so there's also orbital notation. And the outermost electrons are the most important electrons in an atom, so we're going to have what's called a dot diagram to handle those. So you're going to get all four of them right now. And we're going to start with the shell configuration. So electrons occupy these energy levels. If you remember the Bohr model, those are the rings around the nucleus, although that's not what it really looks like. And as far as the electron configuration of these are concerned, well, that's easy. You can find that right on your reference table if you're in New York State. The shell configuration is at the very bottom left corner. So helium has 2, nitrogen 2-5, sodium 2-8-1, calcium 2882, bromine 28187, bismuth, whoa, dash 18 dash? Well, at the bottom of your table, you'll see this little key here that says that a dash denotes the presence of 2-8 for elements 72 and above. The electron configuration is so large, you can't fit all of it in that box. So they just assume the 2-8, and then they give you everything for the third energy level and above. So what this means is helium has 2 electrons in the first energy level. Nitrogen has 2 in the first and 5 in the second. Sodium has 2 in the first, 8 in the second, 1 in the third. Bromine has 2 in the first, 8 in the second, 18 in the third, 7 in the fourth. Bismuth has 2 in the first, 8 in the second, 18 in the third, 32 in the fourth, 18 in the fifth, and 5 in the sixth energy level. I want you to notice something interesting also. You notice how they all start with 2? The first energy level is only big enough to hold 2 electrons. The second energy level is only big enough to hold 8 electrons. The third energy level is only big enough to hold 18 electrons. And the fourth energy level can hold a maximum of 32. So let's look at those 4 energy levels specifically. 2 fit in the first, 8 can fit in the second, 18 can fit in the third, and up to 32 can fit in the fourth. This doesn't mean that this is what they're going to have. This is their maximum capacity. Like, let's say you walk into a restaurant and it says maximum capacity 80 persons. That doesn't mean you have to have 80 people in the restaurant, but you can't have any more than 80 without the health department and fire department coming down on you. Now, these energy levels are broken into sublevels, and these sublevels come in 4 different flavors. We have S sublevels, which can hold up to 2 electrons, P sublevels, which can hold up to 6, D sublevels that can hold up to 10, and F sublevels that can hold up to 14. The first energy level only has an S sublevel. That's why the first energy level can only hold up to 2 electrons. The second energy level can have an S and a P sublevel. 2 plus 6 is 8. That's why the second energy level can hold up to 8 electrons. The third energy level can hold an S, a P, and a D, which is why a third energy level can have up to 18 electrons. And the fourth energy level has all 4 of these sublevels, which is why the fourth energy level can hold up to 32 electrons. So the number of sublevels that an energy level can have is equal to the number of that energy level. And every energy level starts with S. Once S fills up, you move to P. Once P fills up, you move to D. Once D fills up, you move to F. There is something called the diagonal rule to take into consideration how you fill the electrons. 1s fills up, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d, 4p, 5s, 4d, 5p, 6s. It gets really messy the higher up you go because the energy levels actually start overlapping each other. So what this means is that the fifth energy level will start before the fourth energy level even finishes. In fact, here the fifth energy level starts just after the third energy level finishes. So there's a lot of overlapping that happens. So let's look at some examples. Helium. It only has one energy level. And so that's the first energy level. We put a number 1 to represent the first energy level. Now, the first sublevel you're going to come across is the S sublevel. So we write S. And because there are 2 electrons, that is telling us that that sublevel is full. Now, if there was a configuration of 1, you would write 1s1. But because there are 2 electrons, you write 1s2. And that's the configuration for helium. Now, I wouldn't be surprised if you're still really, really confused. So let's keep going. Nitrogen has 2 electrons in the first energy level. The first energy level only has an S sublevel, and it looks like there's 2 electrons in there. That's what it says, 2. Now, the second energy level has 5 electrons in it. We'll write 2 for the second energy level. Every energy level starts with an S sublevel, but an S sublevel can only hold up to 2 electrons. There are 5 electrons in this energy level. The S sublevel only accounts for 2 of them, which means the remaining 3 electrons will go into the 2p sublevel. So we break this energy level apart into 2 sublevels, S and P. 2 go into S, 3 go into P. And 2 plus 2 plus 3 gives us a total of 7 electrons, which is the number of electrons nitrogen has. Still not entirely sure? Oh, well, let's see. Those are the 2 electrons for the S sublevel. And these are the 5 electrons for the second energy level. But just in case, let's try another, bromine. This ought to get rid of any doubts you might have. This configuration is telling us that the first energy level is full, the second energy level is full, the third energy level is full, but the fourth is not. So we can actually write our configuration out quickly. Remember, the first energy level has S. The second has S and P. The third has S, P, and D. S can hold up to 2. P can hold up to 6. D can hold up to 10. So we can actually fill this configuration out relatively quickly. 1s2, 2s2, 2p6. That accounts for the 8 electrons in the second energy level. The 18 in the third energy level are broken down into 3s2, 3p6, 2 plus 6 is 8. We need another 10 for the D sublevel. Now, finally, that last fourth energy level. The fourth energy level always starts with S, like every other energy level, 1s, 2s, 3s, 4s. S can only hold up to 2. That leaves 5 unaccounted for. Those go into 4p. Now, P can hold up to 6, but 2 plus 5 gives us 7. So 4p5 is where the configuration ends. If you're still not entirely sure, I recommend you go back to helium and watch all 3 examples over again. Okay. Those are the 2 electrons from the first energy level. These are the 8 electrons from the second energy level. These are the 18 from the third energy level. And these are the 7 in the fourth energy level. So that is the sublevel configuration. Now for orbital notation. If you think of energy levels as towns and sublevels as streets, then orbitals are kind of like the houses on the street. You see, they get more specific. So when you address something, if you just say, send it to my friend who lives in Cleveland, All right, the letter will get to Cleveland, but where's it supposed to go? 55 Main Street. Okay, but that's an apartment. Which place do we put it to? Oh, apartment 22A. You know what I'm saying? You get more and more specific. Actually, the analogy we're going to use for orbitals is houses with rooms, and each room will be an orbital, and the house is the sublevel. Now, orbitals actually have very specific shapes according to the Schrödinger wave equation. An s orbital is spherically shaped. P orbitals are sort of this weird dumbbell shaped, or two jelly beans side to side. D sublevels, well, those are kind of bizarre shaped. This is kind of cool right there. And then the F sublevels, well, they get just completely freaky. And remember, what these represent is regions of space where you're most likely to find an electron. So, instead of drawing out these obnoxiously complex shapes, we're going to let each orbital be represented by a box. So the orbital is where you're most likely to find an electron, and you can only fit up to 2 electrons in one orbital. You can have 1 electron, you can have 2 electrons, it's even possible to have none. We're going to represent them as boxes, and the electrons will be represented as arrows that go in the boxes. Up arrows represent up spin, down arrows represent down spin, because electrons will spin in opposite directions in the same orbital. Yes, I know, very complicated, so let's get to the examples. The s sublevel can hold 2 electrons. An orbital can hold 2 electrons. Therefore, the s sublevel is just one orbital. The first electron that goes in is an up arrow. The second electron will have the opposite spin, a down arrow. The p sublevel consists of 6 electrons, and at 2 electrons per orbital, that means 3 orbitals exist for the p sublevel. Now, think of this as a 3-bedroom house. First person moves in, yay, I get my own room. Second person moves in, I don't want to share with you, I want my own room. Third person moves in, I don't want to live with either of you, I want my room. So electrons will fill up orbitals one at a time, ups first, until all 3 are occupied. Then, if any more electrons go in, they have to double up. Back to the first orbital with the 4th electron, the second orbital with the 5th electron, and the third orbital with the 3rd electron. D sublevels hold up to 10 electrons, and at 2 electrons each per orbital, that's 5 orbitals. If I have 3 electrons, they'll each go in ups. If I have 3 more electrons, 1, 2, 3. Once all the ups are in, then you can start filling in the downs. If I had 2 more electrons, and finally, if the sublevel was full, that's what it would look like. So the F sublevel can hold up to 14 electrons at 2 electrons each. That's 7 orbitals. Up, 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 up. Down, 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 down. The ups go in before the downs. Now, let's look at that for specific elements. Let's look at helium. This was its electron configuration. So the way you draw its orbital notation is you draw a box and you label it 1s. And now we're going to put the electrons in that 1s orbital. There's 2 of them, up, down. And that's it. That's the orbital notation for helium. For nitrogen, nitrogen's configuration was 1s2, 2s2, 2p3. So our first box will be 1s. There's 2 electrons in there, up, down. The next box is for 2s. There's 2 electrons in there, up, down. P is 3 boxes. Whether you fill them or not, a 3-bedroom house is still a 3-bedroom house, even if only one person lives in the house. Well, there happen to be 3 electrons here, so up, up, up. If there was a 4th electron, it would go down in the first box. And bromine had a configuration of, holy moly, that's a lot. So we had 1s, which is one box, up, down. 2s2 is 2s with one box, up, down. 2p is three boxes, and since there's six electrons, up, 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 down, down, down. 3s is two electrons, so that's a box for 3s, up, down. 3p is six electrons, three boxes, up, 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 down, down, down. That's 3p6. 3d10, p has five boxes, up, 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 down, 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 down. 4s is one box with two electrons, up, down. Now, here's the thing you got to understand. The orbitals will fill up, and every orbital will be full until you get to the last sublevel. The last sublevel does not necessarily fill up. So we're going to do this one a little more carefully. Because P can hold up to 6, and we only have 5 here. So we'll draw our three boxes for 4p and put in first electron, second, third, fourth, and fifth. And that is the orbital notation for bromine. Yes, it's a lot. But when you go on to take college chemistry and learn about hybridization, you're going to be really happy you learned how to do this. Okay, Lewis electron dot diagrams. These dot diagrams are going to be extremely useful to you in explaining how atoms bond together to form molecules, explain the shapes of molecules, and so much more. So this is really what we've taken this whole trip for. The valence electrons are the ones that are responsible for all chemical bonding. You find them in the outermost energy level. And they are always going to be either s electrons or s and p electrons. The most number of valence electrons you can have is 8. And they are either lost or gained during ionic bonding or shared during covalent bonding. Our next unit will be entirely about bonding, and we will be using dot diagrams to explain how the bonding occurs. So let's take a look at your periodic table. What is the highest number of valence electrons that any element has? Well, it's 8. And what two sublevels combined can hold up to 8 electrons? As I said, S and P. And the dot diagrams show the position of these valence electrons, and we use them to predict formulas and the shapes of molecules, which will give us a handle on what the behavior of those compounds is. So here's how you draw them. We're going to put the element symbol in the middle and then use dots to represent the valence electrons. Now, we used arrows with orbital notation. We'll use dots to represent electrons here. The first electron that goes in, well, this is going to require a little bit of explanation. S and P have 4 orbitals between them because S has 1 orbital and P has 3. There are 4 sides around the symbol of an element. Each side will represent 1 orbital. So, for example, this could represent the s orbital. And this side, and this side can represent the 3p orbitals. And electrons will fill in exactly the same way that the arrows filled in your box orbital diagrams. 1 electron is 1 dot. 2 electrons is 2 dots, but because they both go into S, up, down, you put them on the same side of the symbol. Now, you do not have to start on the top. You can start on any side you want. I'm just starting on the top to keep it consistent. -3, the first 2 electrons go in the s orbital, and the third electron goes in a p orbital. Now, you can go to the left or the right. I'm going to go to the right for this example. 4 valence electrons, the first 2 fill up s. And remember, p fills up 1 orbital at a time. This side is 1 orbital, this is the next orbital, and this is the next orbital. The 3 orbitals for p, which means if it's -5 and there are 3p electrons, the first 2 go together and then up, up, up. Now, you see how these electrons are not paired together? These two are paired, but these are unpaired electrons. It's these unpaired electrons that are shared during a covalent bond. So this is telling me that this element here can share 3 electrons to make a compound. There's a lot you can tell just by looking at the dot diagram. With 6 valence electrons, there are 2 electrons in the s orbital, and there are 4 in the p, and they go in the same way they went in those 3 boxes: up, 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 and then back to the first orbital, down. I'll show you that again. Up, 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 down. This gives you 2 unpaired electrons, so 2 bonds can be formed. -7, the first 2 electrons go in s, and then p fills up with 5, up, 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 down, down. And I think you can figure out how 8 works. Up, 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 down, up, 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 down, down, down. A fully completed stable octet. Any atom with a stable octet will not be chemically reactive. All the elements in group 18, check it out, go to your periodic table. Every element in group 18 has -8, except for helium, which is -2, but that's fine. Any element with a stable octet has what it wants and has no reason to chemically react. That's why they're called noble gases. They don't react with other elements because they already have what they want. In the next unit, I'm going to show you how atoms gain or lose electrons or share electrons in such a way that they end up with 8 valence electrons. So let's apply this to actual elements. Lithium has 1 valence electron, so that's its dot diagram. Beryllium has 2 valence electrons. That's its dot diagram. Boron has 3 valence electrons. So, up, down, up. Carbon has 4 valence electrons. So, up, down, up, up. Nitrogen has 5 valence electrons. Up, down, up, up, up. Oxygen has 6 valence electrons. Up, down, up, 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 down. Fluorine has 7 valence electrons. Up, down, up, 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 down, down. And finally, neon has 8 valence electrons. Up, down, up, 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 down, down, down. By the way, carbon, when it forms chemical bonds, doesn't stay this way. When carbon forms bonds, in order to make a stable octet, one of the s electrons gets excited up to this empty p orbital. But we'll talk about that more when we do bonding in the next unit. So one dot by itself on one side is an unpaired electron, and these are the electrons that are shared during a covalent bond. And all bonds are formed so that atoms can end up with the same electron configuration as a noble gas, a stable octet. Now go ahead and try a bunch on your own, and I think you're going to have fun doing it. And we're going to be using this over and over and over throughout the rest of this year. So once again, I wish you well, be swell, and until next time,